Following the two tests that we've done on David's car, I thought it appropriate to bring the subject completely up to date and talk a little about CAN and how you can use this tool to look at CAN network and the communication packages, if you like, the messages, telegrams, which are transmitted on CAN. CAN presents a unique problem because it's a very high frequency signal, and you need a high performance scope. In other words, a sampling rate must be very, very high to add great detail to the actual CAN message. The other challenge is that having captured the signal, you need to expand and zoom in to look at a large amount of time. In other words, if you're looking for intermittent glitches, and I can actually put intermittent glitch on this signal. You may notice I'm using a simulation board. Now, there's no disadvantage in me displaying this technique on a simulation board because the CAN protocols are an international standard. The type of signal that this board is generating is absolutely identical to the signal you'll find on a CAN high, CAN low network. So you're at no disadvantage seeing this as a simulation on this board. I've initially set the tool up. There's a couple of ways you can go into CAN. You can click on the automotive icon in the toolbox and pull down the menu and select CAN. There are three options within that program. I've chosen to put up a screen time of 50 milliseconds per division. And what you can see now is several packages of CAN data across the screen. It's highly compressed and diagnostically has no detailed meaning. What I'd like to do, just briefly, is let you take a look at this and then switch a glitch in. And what you're going to see is the same effect as if there was a fault within, a genuine fault within an automotive CAN network. These sort of faults are brought about by inductors, coils, ignition devices, power seats, anything that has a fair amount of current running through them that's being switched very quickly, and it causes spikes or ringing on the CAN network. And if that happens, the CAN message then becomes corrupted and the intended functionality of that message is then destroyed. In other words, the vehicle will not demonstrate that command that's been intended by the driver. So let me switch now this glitch. You notice now fairly tightly compact telegrams with no apparent error. I'm going to put the glitch in. Straight away you can see the effects of that. These additional spikes that now appear on the screen is high frequency induced errors, or simulated high frequency induced errors, that would cause corruption and chaos to the CAN messages, would cause rejection of message and the possibility that that entire network would shut down because it can't understand the messages that are being transmitted, with potentially catastrophic effects within that particular network. So what do we need to do now? We need to look in detail. We need to zoom in on this, and this is where the true power of the memory of this particular scope really comes into its own. So first of all, I'm going to freeze the image, and I'm not going to change the time base. Traditionally, you change the time base, and that's one option you've got, of course, is to set a unique trigger up. I could, for example, set a trigger up within the glitch field, in other words, within the parameters where the glitch exists, which is outside the data field, and that trigger then will capture that. But I'm going to use it simply by using a magnifier, and by going up to this toolbox, I can now select anything up to 2,000 times. I'm going to pick a fairly sensible magnification of, say, 50 times. And when I select that, we now have expanded into the data buffer, and the memory buffer would go several hundred feet left and right of the screen. I need to go now find the package, the CAN message or the glitch, and to do that I can navigate left or right by engaging that icon in the corner and using the enter key, and I'm simply just going to roll this data. There we go. Here we now have seen 3 of those glitches now in much more detail. Now the other technique that we could use, if this was a real event on a car and this was being caused by a device, we've got 4 channels on scope. I now would have 2 other channels free. We're only using 2 channels at the moment, CAN high, CAN low. We could use the other 2 channels to test the type of components that would cause this type of induced error. Ignition coils, power seats, I've already mentioned. So I could connect those other two channels to those devices to see if there's a similarity. In other words, there would be a synchronization of the event of switching a component on. You could use current measurement, if you like, as one option, or voltage, and we're looking for spikes or large current, what we call current dumps, to cause this type of interference. If I carry on with this, there we see the CAN package in great detail, and we can see that that particular package is free from interference, that the interference we've just experienced did not affect this particular message. And indeed, I can go on searching for an incredible amount of time. There we see another error, a single error this time. Once again, it's not corrupt that particular message package. And you get the idea that we can use an enormous amount of this memory to zoom in and examine these CAN packages in very, very much great detail. The other option, of course, is to go back into the magnification drop menu, go back to ×1, the original, and run the scope and reduce the time base. This time I'm going to use 10 microseconds. What you've got here is 1 bit, and we still have a very, very high sample rate. So I'm using that very, very high sample rate to examine one event only. And you can see the actual ringing. The ringing's caused when devices are switched off. You can see that the very high bandwidth now that we're looking at, coupled with a very high sample rate, gives an incredibly accurate package. And if the transmission of CAN was being, or the failure of transmission of CAN was being caused by a wiring problem or a hardware problem, you wouldn't see these very clean, precise verticals. They tend to round the corners off. And what they call the rise time. The rise time here is absolutely vertical, absolutely spot on. If the rise time were lazy and it's an oblique angle, that then would be a problem. The computer cannot read those type of transitions. They've got to be absolutely precise. So an incredible amount of detail by manipulating time and using memory. Other issues, of course, with the motor vehicle that cause these types of errors, the manufacturers now are adding more and more computers, more and more controllers on various networks. I've already mentioned we can have up to 6 networks. A network can become saturated with data at around 35-40% of the baud rate. So it's an incredibly low threshold before we get rejected messages. And I predict, in fact, not just predict, it's actually happening now, many of the large manufacturers have an enormous problem with CAN transmission data affecting the functionality of the vehicle, where messages are being rejected, you get routine skip, events happening on the car that were never intended by the driver. And all of that needs debugging, and this goes way beyond serial capability. We're going to need a scope with this type of performance and this type of memory, so it's an absolutely ideal tool for this task. And it's well worth bringing within this instructional video that it's brought in. It really brings everything completely up to date. And of course, whether you've got the experience and confidence to use this in LabScope, which I've just done, or to simply go straight to the automotive window with the pop-down menu, it certainly gets you off straight away.